Today I will talk about connections in the tangent bundle. When I define a connection, I consider a smooth vector bundle over a smooth manifold M, and we define the connection as a map defined on Km times gamma E with values in gamma E, where this symbol denotes the sections, the smooth sections of this vector bundle. Starting from today, we will work with E equal Tm. This means that the connection that we get is called connection in the tangent bundle, and this will be a map from Km times Km with values in Km, because the sections of the tangent bundle are what we call vector fields. Now let's see how a connection looks like in terms of a local frame. So let E1, E2, En be a smooth local frame for Tm on the open subset U. Then we can write first values of I and j, nabla ej along EI as a vector field having the following property: the component functions along EK is denoted by gamma I j k. Of course, here I am using Einstein convention because there is a sum on the index k which has been omitted, and gamma I j k from U with values in R are what we call connection coefficients of nabla with respect to the given frame. These connection coefficients completely determine the connection in the open set U, as this proposition says. So let M be a smooth manifold with or without boundary. Let nabla be a connection on the tangent space Tm supposes before that E1, E2, En is a local frame. Over a U open subset of M, and let gamma ij k with ij k equal to 1 to n, where n is dimension of M, be the connection coefficients of nabla with respect to this frame. Then if x, y are smooth vector fields on U, such that x is given by xi, ei, and y is a yj, ej, then nabla y x can be written as x yk plus xi yj gamma ij k times k. The proof is a computation so nabla y x, this is nabla x of yj ej, and the connection nabla satisfies the product rule, so this is x yj ej plus yj nabla ej along x, but x can be written as xi ei and now I use the linearity and here I use the definition of gamma ijk. Now if you want to write this formula in this form, you just make a change of index here. You replace j by k, and you factor out x yj plus xi yj gamma ijk, and you will get this formula. So if you know gamma ijk, you can compute the value of nabla yx for any arbitrary pair of vector fields on an open set of the manifold. Now we want to answer the question, do connections exist? Because so far we did not produce any example of connection. There is a trivial example. Which is the Euclidean connection that is we work in Rn. We can define nabla bar this way: nabla yx equal xy1 ddx1 plus xyn ddxn, where of course we are assuming that x1, x2, xn are the coordinates on Rn. Consequently, the frame, which is actually a global one, not a local one, is ddx1, ddx2, ddxn, and y is y I ddx I. A more interesting example is the one of the tangential connection on a submanifold of Rn. Precisely we consider an embedded submanifold of Rn, and we define nabla T by this formula, where pi t is the orthogonal projection onto Tm, and x tilde y tilde are extensions of x and y. To an open set of Rn. It is possible to prove that this is a connection, so you have to prove that this formula makes sense, that this is C infinity linear in X, R linear in R, and it satisfies the product rule. I leave the details to you. I prefer to pass to the presentation of this lemma, which says that there exists a one-to-one correspondence between connection in the tangent space Tm and choices of n-cube smooth real valued functions gamma ijk on M. So suppose that M is a smooth manifold of dimension n with or without boundary that admits a global frame E1 En, then the formula nabla yx given by x y k plus xi yj gamma ij k dk now gives a one-to-one correspondence between connections on Tm and choices of n cube smooth real value functions gamma I j k on M. Okay, let's see the proof maybe. So it is clear that a connection determines the functions gamma I j k because you have the formula nabla ej I equal gamma I j k ek. And the previous proposition, let me be precise, the proposition which says that gamma I j k completely determine no, sorry. The proposition I want is not this one. The proposition which says that gamma ij satisfy nabla x y equal x yk plus, I think I need more space, so I will copy again, nabla x y equal x y k plus x I y j gamma I j k ek. And on the other end, given gamma I j k, we can define a connection nabla by this formula. It remains to prove that nabla is linear in x and y, smooth and it satisfies the product rule. Now let's see that the tangent bundle of every smooth manifold with or without boundary admits a connection. So this proposition says that if I give you a tangent bundle, I can produce at least one example of connection. So suppose that this is a set of coordinate charts for M. Previous lemma implies that there exists a connection nabla alpha on U alpha. Why? You just need to choose n cube function gamma ijk on U alpha. It's possible to prove that a smooth manifold is paracompact, and this means that if you choose a partition of unity phi alpha subordinate to the cover U alpha, you know that the support of phi alpha form a set which is locally finite. The reason why we want to work with the partition of unity is that we can glue together these connections which are defined locally. So how this is done? We define nabla yx as sum on alpha phi alpha nabla x alpha y. This formula makes sense because this sum here has only finitely many non-zero terms in a neighborhood of each point, and this defines a smooth vector field on M. Also in this case, it is necessary to prove that This is a map which is linear in y and x, and it satisfies the product rule. Let's skip the proof of the linearity because I think it's not interesting. Instead, let's see how to prove that this is actually a connection. In particular, it satisfies the product rule. I want to mention that in general, when you have the sum of two connections, you don't get a connection, because in general the product rule is satisfied, but this is actually a connection. So we have to prove that nabla fyx, this is xf y plus f nabla yx. So this is sum on alpha of phi alpha nabla alpha x f y. This is a connection, so I can write sum on alpha of phi alpha of x f y plus f nabla alpha x y. And this is just x f y sum on alpha phi alpha plus f sum on alpha phi alpha nabla alpha x y. But this is 1, so we get x f y plus f nabla y x. Please observe that it is very important to work with a partition of unity, and one reason of this is that this term disappears because it is equal to 1. Now let's talk about vectors and tensor fields along curves. So suppose that M is a smooth manifold with or without boundary. Then given a smooth curve gamma on M, a vector field along gamma is a continuous map sigma, V, from I with values in Tm such that the value of V at T belongs to T gamma Tm for every T in I. It is smooth if this map it is smooth. We use this symbol for the set of all smooth vector fields along gamma. You can prove that this is a real vector space, so real vector space equipped with the pointwise vector addition and multiplication by constants. And it is also possible to prove that it is a module over C infinity I with the multiplication defined pointwise by the following formula: fxt, this is equal to f of t xt. A simple example: take the velocity vector of a smooth curve. Gamma prime t clearly belongs to T gamma T M. Another example is given by the normal vector to a plane curve. If you have gamma with values in the Euclidean plane, then you can define this normal vector as the rotation by 90 degrees in the counterclockwise direction. Another example, actually it's a class of examples, can be constructed as follows. Suppose that gamma is a smooth curve with values in a smooth manifold M, and V tilde is a smooth vector field on an open set of M which contains gamma I. Then we can define a smooth vector field along gamma writing Vt equal V tilde at the point gamma t for each t in I. It is clearly smooth because gamma is smooth and V tilde is smooth. We take advantage of this example for giving the definition of extendable smooth vector field. So a smooth vector field along gamma is extendable if there exists a smooth vector field V tilde on a neighborhood of gamma I such that Vt is V tilde at gamma t. So clearly this vector field here is extendable Now, a few words about the definition of tensor field along gamma. A tensor field along gamma is a continuous map sigma from I, which is the interval of definition of gamma, to tk L Tm, such that sigma t belongs to tkl T gamma t m. For each t in I. It is smooth if sigma is a smooth map, not only continuous. Also, in the case of tensor fields, it's possible to give definition of extendable tensor fields. So a tensor field is extendable if there exists a smooth tensor field sigma tilde on a neighborhood of gamma I such that sigma, the tensor field along gamma, is just sigma tilde composed with gamma. Now let's introduce an important object. It is the covariant derivative along a curve. We have the following theorem. So let M be a smooth manifold with or without boundary, and let nabla be a connection in Tm. Then for each smooth curve gamma in M, the connection determines a unique operator denoted by dt, defined on key gamma with values in key gamma, which is called covariant derivative along gamma such that one dt of AV plus BW is A dTV plus B dTW for any AD in R, VW in T gamma, 2 dt of F times V, this is F prime V plus F dTV, so this is the product rule for any F in C infinity I and V in T gamma. Three, if V in T gamma is extendable, then for every extension V tilde, we have that dTV T is nabla V tilde along gamma prime T. Similar statement for an analogous operator on the space of smooth tensor fields along gamma. Okay, let's try to prove this result. So let's start by the uniqueness of the covariant derivative. Okay, suppose that dt is an operator satisfying the properties 1, 2, 3. And fix the 0 in I. I is the interval on which gamma is defined. We proved that in the past that the connection depends only on the values nabla yx. We prove that a connection satisfies the following property. The values of this connection at a point depends only on the values of y in a neighborhood of that point. Using the same argument of that proof, of that lemma, you can prove that dTV at t0 depends only on the values of v in a neighborhood of t0 that is t0 minus epsilon, t0 plus epsilon. You could ask the following question: what happens if t0 is an endpoint of I? In this case, you have to extend the definition of gamma to an interval which is open and contains I, and you can apply the argument that I'm going to present. So now choose smooth coordinates x1, x2, xn for m in a neighborhood of of gamma t0 in m. Then this means that we have in this neighborhood the frame delta 1, delta 2, delta n, and Vt can be written as Vj at t, Vj at gamma t. For t near t0 with Vj smooth real functions in a neighborhood of gamma t0. Sorry, not gamma t0, but just t0. These are functions of t, so I have to work in a neighborhood of t0. Sorry. Then I'm assuming that the operator dt satisfies the properties 1, 2, 3 of the theorem. So this means that I can compute dt of vt, and I can also use the fact that these are extendable vector fields. So this is dt of Vj dj gamma t, and by the product rule this is Vj dot this is the derivative of Vj with respect to t plus Vjt null dj gamma t gamma prime t. So to get this formula I use the fact that dt satisfies the product rule, and I'm using the fact that these are extendable vector fields. And now I can expand this term using the gamma ijk functions. So this is v dot k t. Here I made just a change of index. Instead of working with j, I use k, plus now I want to manipulate this term here, and I write gamma prime t as gamma dot I d. Let's use di. Okay, di gamma t. So you will use the linearity of nabla, and you will get gamma dot I Vj and now you have nabla d delta I delta j, which is gamma I j k multiplied by delta k restricted gamma t. So this formula says that this operator is unique, because once you fix your connection, you have a specific set of gamma ijk functions, and this is a uniquely determined formula. Now we have to prove the existence of the covariant derivative along a curve. So suppose that gamma I is contained in a single chart, then we can define dTV by this formula, it is necessary to show that dt satisfies a 1, 2, 3, the properties 1, 2, 3 of the theorem. I leave this as an exercise for you. Instead, if gamma I is not contained in a single chart, then we define dTV on each chart by a star, the same formula used here and that I erased, and then you use the uniqueness we already proved for proving that the various definitions agree when the charts overlap. And the last result I will present today is a proposition about the connection nabla. Essentially what I want to prove is that if you want to compute nabla y along V, where V is a vector, then this one is a vector is a vector which depends only on the value of y along any curve which passes through the point P and whose velocity vector coincides with V. So the statement of the proposition is the following. Let nabla be a connection in Tm, where M is a smooth manifold with or without boundary, and V in Tpm, where P is a point of M. Then suppose that y tilde are smooth vector fields which agree at points of a smooth curve. Such that gamma 0 is P, sorry, let's choose T0. And then you have that nabla y along V is equal to nabla y tilde along V. The proof is easy. We define Z in T gamma by this formula, Z at T equal Y along gamma T, which coincide with Y tilde gamma T. Now we use previous theorem, the theorem about the covariant derivative along a curve. Precisely, we have that Z is extendable and Y tilde and Y are its extensions. Then you can use the statement number 3 of the theorem. Let's say property 3. It was the following: V extendable implies dt with t equal nabla gamma prime t v tilde. Then if I use this formula, where instead of v I use z, and instead of v tilde I use y tilde and y, I get that dt0 dt0 z at t0, this is nabla gamma prime t0 y tilde, that is nabla y tilde v, at t0, so I should write this, but you have also that sorry for the typo, this is just dt. So this means that nabla v y t0 is nabla v y tilde t0, but t0 is arbitrary, so nabla v y coincide with nabla v y tilde, which is exactly what we wanted to prove. It's a good point where to stop. Thank you for your attention.